So we've been talking about, or we should be talking about, finding critical points and classifying them, and then also talking about global maxima and minima on a limited domain is what we're doing right now. So let's look at this function. Let's say we've got f as a function of x and y, and it's equal to x to the fourth plus y to the fourth minus 4xy plus 2. And we want to find and classify the critical points. And we don't typically call them critical values because it's not that they're just a value, right? They're actually points, right? It's an XY coordinate. Is it hard to see?
Yeah. Well, I forgot my glasses.
Oh, okay. If it's easier to see, you can always hop on Zoom and try actually looking at it closer that way. It might be easier. I don't know if it's actually easier, but it might be. I will also say all the words. So our function is x to the fourth plus y to the fourth minus 4xy plus 2. So first things first, we're going to find the critical values. Now, I am used to doing this in the following way by just writing down what the partials are. So fx is 4x cubed minus 4y. Fy is 4y cubed minus 4x. He might prefer you write them as a gradient. It doesn't really matter. The gradient's literally just the same thing. It's fx fy, which is 4x cubed minus 4y cubed minus 4x. Although I will say the one thing about writing it this way is it might be slightly more, it might be extra clear that both things have to be 0 at the same time. Whereas when you write it here, it might not be so clear that, oh yeah, we need x and y, or we need both fx and fy to be simultaneously 0. So what I mean by that is, sure, for example, in this first equation, this isn't going to be a critical point. I just want to point out, in this first equation, it would totally work to have x equal to 2 and y equal to 8. That would totally make the first partial equal to 0. Does that work for the second one? If x is 2 and y is 8, you're going to get a really big number, 4 times 8 cubed minus 8, which is not 0. So I want to point out the fx at 2, 8 is 0. Fy at 2, 8 is not. 2, 8 is not a critical point. So we are looking for the points that make both fx and fy 0 at the same time. Let me go ahead and all right, so how do we do this? Well, this one's actually a little tricky. You might correctly guess that 0, 0 is a critical point, right? Usually you can safely kind of test it for points, but okay, 0, 0 seems to work. But we want to be exhaustive, right? 0, 0 is a critical point. Is it the only one? Probably not. There's probably others. So usually what you need to do is, there's no really good way to say this. What we need to do is kind of find all the ways one can be 0 and then plug this into the way the other one can be 0. And I feel like his question is actually a better example of this than this one, but we'll get there. Don't worry, we've got more examples. So what I'm going to do, since there's no real there's no one solution, right? I can't just say x equals 1 and this thing is 0 or this thing is 0. I have to have an x and a y together because I don't have something like this problem we did last time. Let me just show you, or this problem we kind of did last time, which is similar to this, where we had a function like this, 2x squared minus y squared plus 4x plus 6y plus 1. And when you found the partial derivatives, you just got x equal to -1, and you didn't have to think about y in that equation and y equal to 3. Right? There wasn't any having to be like, oh, x is this when y is this, whereas this function is different. It's work a little harder here. So I'm going to take this. I'm going to solve for something convenient. Well, okay, 4x cubed minus 4y equal to 0. Let's isolate y. So 4x cubed equals 4y. Y equals x cubed, or x cubed equals y. And now I'm going to plug that into the other equation. So my other equation, I'm going to jam that in there. So I'm going to say, okay, I'm going to have 4 times x cubed minus 4 times x equal to 0. Great. I've got an equation with just x's. I should probably be able to solve it. So let's factor out a 4. Or you can divide both sides by 4. That's equally good. You can divide both sides by a constant. It's dividing both sides by a variable that's dangerous. So I've got 4 times, let's see, x cubed is x to the 9th minus x. Let's say I also could have factored out an x. I've got 4x times x to the 8th minus 1 equals 0. So what are my possible values for x? X equals 0 is definitely 1. What else? I meant to not write that. I meant to actually have you guys say the things. What's the last one that I'm not going to actually write? -1, right? -1 to the 8th power is still +1. So those are the 3 values. And we know that y has to equal x cubed. So if x is 0, y is going to be 0. If x is 1, y is going to be 1. If x is -1, y is going to be -1. Thanks. So my 3 critical points are 0, 0, 1, 1, -1, -1. Now we have to classify. Meaning we have to find, oh yeah.
Why is it 0, 0, and 1, 1?
So
Like if we had solved if x were to be equal to 2, for example,
right.
would a critical point be 2, 2?
No. Here's why. If x is 2, so here's the thing. If x is 2, this equation will never equal 0. And so we have to be really, this one, right? This one is a little bit more challenging. Right? It has to be true, right? We looked at this equation. We need this to equal 0, right? Oh, sorry, you can't see that. We need this to equal 0. So that means if x is 2, y has to be 8. Right? There's no other possibility if x is 2 for this one to be 0. And maybe I've got those slight. Oh no, I'm sorry. We used this one. I apologize. And we're plugging back into this. We used this one, so it's actually less nice, but it is still true that if x were to be, I feel like I'm saying bonkers things here. Oh, that's right. Yeah. If x were to be 2, like we said, right, y would have to be 8. According to this, right? We said this has to be 0. And the only way for that to be 0 if x were to be 2 was for y to be 8. Cool? But then the problem is, if x is 2 here and y is 8 there, that's not a solution to this equation being 0. So we really have to insist that any solution to this being 0 also has to be a solution to that being 0. And because we're looking for where the gradient is equal to 0. The 0 vector, right? The fy and fx are both 0 at this point. And so the only solutions we get are these ones because they're the only ones that actually make it work. We couldn't get 2, 2. 2, 2 doesn't actually satisfy either one of these. We'll do more practice, but I really want to emphasize, right? We're just looking for the points that make this 0 and this 0 at the same point. Okay. So then we're going to check them, or we're going to, I should say, we're going to try and classify them by finding capital D. You can just call it capital D. I will probably say every time it is the determinant of the Hessian matrix, whatever. It's capital D. It's fxx, fyy minus either mixed partial, doesn't matter, fxy squared. So let's see. We need our fxx and fyy, or excuse me, fx and fy. Go there for a second. So fxx is going to be 12x squared. Fyy is going to be 12y squared. And fxy or fyx is going to be -4. So writing this out, I'm going to get 12x squared times 12y squared minus -4 squared. And generally, I don't really think you need to simplify this. Now, this one's not hard to simplify, right? You could totally multiply this out as 144 x squared y squared plus or minus 16. But if it's more complicated, maybe if it's not, our job here is only really to tell if this quantity is positive or negative. Multiplying it out and expanding it might actually be detrimental. It might not be helpful. It might make it harder. So I would encourage everyone to typically leave it as this times this minus that thing squared, and then just try and plug in your points. So if we're going to plug in 0, 0, I'm going to get 0 times 0 minus 16. I don't care that it's negative 16. I care that it's negative. When this thing is negative, that means we have a what at our critical point? Is it a max, a min, or a saddle? It has to be, well, so if I'm not doing more work, it means it's a saddle, right? Because if it was greater than 0, I'd have to do an additional step and check and see if it's a maximum or minimum. So it's always 100% the case that if this quantity is negative, you have a saddle. Let's look at the other critical points. Let's look at 1, 1. So plug in 1, 1, I'm going to get 12 times 12 minus 16. I don't care what that number is. I know it's positive. It's 144 minus 16. Yeah, it's positive. Great. So when it's positive, you have to do another step. So it doesn't matter which one you check. And so I want to point out, if this thing is positive, it means this part here was bigger than this part here. It's always going to be this thing minus that thing. And the second thing is always already going to be positive because it was something squared. So this is always positive, meaning that if this entire quantity is positive, this had to be bigger, meaning it had to be positive. And the only way things multiply together and end up being positive is if they're both or both positive. More generally, they're both the same sign. So if this is positive, these are the same sign, meaning you only have to check one of them. Because what we're going to do is we're going to check the sign of either fxx or fyy. But they have to already be the same since this thing is positive. So when we do that, well, they're both 12, right? That's another good reason to not actually multiply this all out, because we can already see, oh yeah, I already know that fxx is 12. Great, my second derivative is positive. That means we're concave up, which means we have a minimum. So second derivative positive, concave up, we have a minimum at 1, 1. Okay, we got one more point to check. -1, -1. So if I plug in -1, -1, I'm going to get the same thing. I'm going to get 12 again, times 12 again, minus 16, still going to be positive. And we can also see that when we plug in -1 to either second derivative, right, fxx evaluated at -1, -1 is just 12, which is still positive, meaning we are still concave up, meaning we still have a minimum at this point as well. in case you're curious. One sec. No, I don't want to. Sure. I should have said that. This looks like no, you can't see it. So looks like that. And I think you can pretty easily see, oh yeah, there's two minima there. And if we swirl this around a little bit, you can see that that point kind of like, I mean, it kind of looks like a pair of pants, right? Kind of looks like a pair of pants, and not to be too graphic, but in the crotch, there's a saddle, right? It comes up this way and goes down, and then, right, like up that way, and then that's terrible. Okay, so you can see it on the thing, right? There's the relative maximum that way and the relative minimum that way. So it's a saddle point. Kind of cool. I think it helps to see the things. All right. Questions? All right, let's look at another example. Yeah, let's look at another example. Oh yeah, I had an example. An example that's similar-ish to your first homework question, but not too similar. Or what did I come up with? I remember what it is. It's f of xy equal to x squared minus y squared minus 4 quantity squared. And we want to find critical points and classify them. Now, like your homework problem, I will tell you this function has an infinite number of critical points. You might not have seen that about your homework question yet, but it does. We'll circle back to that, but we'll circle, pun intended, back to that. So I know it's lame, but that's what I've got. So I'm taking my partials. 2 times x squared minus y squared minus 4 to the first times the derivative with respect to x, which is 2x. And then my partial with respect to y is very similar. It's 2 times x squared minus y squared minus 4 to the first times 2, so negative 2y. And we want to see where each of these is 0. So actually, I should be more specific. We want to see where both of these are 0 at the same time. That's what I really want. And we can identify a couple points, but here's the idea. And let me actually give you, we're going to come back to this in just a second. Let me give you an easier example of what I mean. I'm going to make up some pretend functions. Let's say that we took some partials, and we got the partial with respect to x was x minus 2 times y plus 4, and the partial with respect to y was, let's see, don't make this stupid, James. Okay, x squared minus 9 times y minus 1. And I want to find all the critical points. So what's a way this could equal 0? What could x be? X could be, or y could be great. So if x is 2, well, then x has to be 2. But here y could be 1. So if x is 2, then fy is going to be 4 minus 9 times y minus 1. And if I want that to be 0, I have to get y equal to 1. So the critical point here would be 2, 1. Or if I want this to be 0, y could be negative 4. So if y is negative 4, then I have to plug that in here. And I get x squared minus 9 times negative 4 minus 1 equal to 0. That can't be 0, but this can. X could be plus or minus 3. So my critical points from this part, or from this selection, are going to be 3, negative 4, or negative 3, negative 4. And each of these 3 points makes both of these partials 0 at the same time. Right? If you plug in 2, 1, you get 0 here, you get 0 there. Done. You plug in negative 3, negative 4, you get 0 there, you get 0 there. They're both equal to 0. So typically, sorry, you couldn't see what this point is. Typically, when you're trying to find where these partials are equal to 0 simultaneously, it's a process of kind of setting all the factors equal to 0, and then seeing, oh, if I make this factor 0, what does the other partial have to be? If I make this factor equal to 0, what does the other partial have to be? So let's go back. So I'm going to start off easy. I'm going to start by saying, well, x could be 0. Then either, well, I could also just have y being 0, right? That would totally work. Oh, sorry, someone wrote something. Sorry, there was a couple questions back there. How did I get fxx equal to 12x squared? Yeah, yes, so fxx was 12x squared, sorry. Just one quick second. Fxx was, like, did I make a mistake? I hope not. Oh, no. So fx was 4x cubed, and the derivative of that, or sorry, 4x cubed minus 4y, and the derivative of that was 12x squared minus 0. And then I got 12 when I plugged in, because I was plugging in the point 1, 1, or negative 1, negative 1. So when I plugged in negative 1, negative 1 into 12x squared, I got just 12. Hopefully that clarifies things a little bit. All right, so 0, 0 is one of my critical points. If x is 0 and y is 0, this whole thing is 0, this whole thing is 0. But instead of picking x equal to 0 and y equal to 0, I could pick x equal to 0 and all of this equal to 0. Or did I pick something dumb? So sometimes you don't get an answer. That's okay. So this one, I think we're actually not going to get an answer, which happens sometimes. Well, let's see. If we plug in 0 for x, we're going to get negative y squared minus 4 equal to 0. And I don't think that actually has any solutions, because you'd have to have negative 4 equal to positive y squared, and that is a no-go. That happens sometimes. It's okay. Let's look at what happens if we pick y equal to 0 and the other one, x squared. It's the same thing, right? And x squared minus y squared minus 4 equal to 0. So here, if y equal to 0, that means we have x squared minus 4 equal to 0. So we get x equal to plus or minus 2. So the critical points we get from this selection are 2, 0, and negative 2, 0. Now I'll point out that this work is actually, I don't want to say repetitive, but it's actually slightly unnecessary. I still think it's good to do to see the process of how we typically do this. But what we're going to see is that we can also set this part equal to 0 and this part equal to 0, which I know are the same. But the point is, if both of these are 0, then both of my partials are 0. So all I really actually need to get both of these equal to 0, or in other words, to get the gradient to equal 0, is for x squared minus y squared minus 4 to equal 0. And I could say the same thing again, and x squared minus y squared minus 4. It seems silly to write the same thing twice. And any point that satisfies this is a critical point, which there are literally an infinite number of. I'm going to list a couple of them. X could be 3, and y could be something lame, like the square root of 5. It's not lame. Square root of 5 is a perfectly fine number. And really, either one of these could be positive or negative. So really, I should say, actually, plus or minus 3, comma, plus or minus root 5. Right? Because if x is 3, you get 9. If y is root 5, you get 5. And 9 minus 5 minus 4 is 0. So already I just added 4 critical points. Positive, 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 negative, negative, positive, negative, negative. And there are an infinite number more, right? I could go one bigger and go x could be plus or minus 4, and then that's going to be 16. I need to subtract 12, so y could be plus or minus root 12. I don't want to test. Not only do I not want to, I can't test every single point if there's an infinite number of them. It's okay. We're going to make it work. But I just want to point out that if you have the same factor occurring in both of these equations, that means any solution to that being equal to 0 is a critical point. So let me graph the critical points for you. So here's my XY plane. Now I wish I had picked this. I didn't want to pick a circle because the circle is what you guys have in your homework problem. But yes, you have a whole circle's worth of critical points in your homework problem. The circle x squared plus y squared equal to 1. Here we have the point 0, 0, which is not on the circle. I mean, not on the thing we're graphing, right? Because the other thing we have is we have all the points that satisfy x squared minus y squared minus 4 equal to 0. Which these two critical points that we already found, 2, 0, and negative 0, are on that curve. And now I'm just going to draw it. Like, and this is not really the point of this problem, right? It's not to draw this, but I just want to show you. Oh, yeah. Here's all your critical points, all infinity of them. Don't worry, it's not as bad as it seems. So how are we going to check these? Well, we can still find D in the usual way. But I will point out, right, if you're talking about like listing the critical points for this, you really have to say something like, oh, my critical points are 0, 0, and I guess you could write out 2, 0, and negative 2, 0 if you want. And then all points that satisfy that equation. So there's my list of critical points. There's a lot of them. All right. Oh yeah, we're going to find D, the determinant. So let's look back at fx. Ooh, fx is not lovely. I really would prefer not to use the product rule if I could help it. I can help it, right? This is not terrible to multiply out. So if I can avoid using the product rule by doing an easy multiplication, I should. Let's rewrite things. So I'm just going to look over here for real quick. Fx is 2 times x squared minus y squared minus 4 times 2x, which we multiply out, 4x times x squared is 4x cubed, 4x times negative y squared is negative 4xy squared, and 4x times negative 4 is negative 16x. Fy, which was 2 times x squared minus y squared minus 4 times negative 2y, is going to be a negative 4y times x squared. And negative 4y times negative y squared. And the negative 4y times negative 4. All right. So now let's use that to find our second partials. So fxx is going to be, sorry, I'm trying to make sure I pay attention to the chat too, in case you guys have any questions. I am. I just, if I don't see the chat and like you have a burning question, you can unmute yourself and say words. It's really okay. Except then you would be identifying yourself. So you say, hey, James, there's a question. All right. So fxx, 12x squared minus 4y squared, ooh, minus 16. Oh, but we're not. I was like, oh, that's terrible. It's not terrible. I was thinking we're going to have to set this equal to 0 and solve. That's not what we're doing. We're just plugging in our critical points. And then fyy is equal to negative 4x squared plus 12y squared plus 16. And then fxy is hopefully the same. If they're not the same, we've made a mistake. But fxy is 12, not 12. Fxy is negative 4x times 2y. So negative 8xy. And that's it. And it should be the same here. If we take the derivative of this with respect to x, yeah, you get negative 8xy. So check. All right. So now we want to classify. And we've got 1 point all on its own. Oh, sorry, you guys. We got 1 point all on its own, 0, 0. So let's try 0, 0 first. I guess we should write out what D is. So D is, and this is an example of you should not multiply this out. definitely don't multiply that out. You might, no, I don't, well, we'll see. So let's evaluate D at 0, 0. So let's see, 0 minus 16 times 0 plus 16. E minus, oops, -8 times 0 squared. That's going to be negative. It's negative 16 times positive 16 minus 0. That's negative something. I don't care. It's negative. Which means we have what? We have a saddle. That's fine. Yeah. I'm sorry, I was just thinking about the graph of this function. Anyway, we'll take a look at it. I think I wasn't zooming out enough to see that. All right, anyway. So a saddle there. All right. So now we could try plugging in 2, 0, negative 2, 0, which is kind of repeating the work, but let's go ahead and just do it for one of them so we can see what's going to happen. And when you plug in 2, 0, all right, let's see what I've got here. I'm going to have 12 times 4, which is 48, minus 4 times 0, minus 16. I'm a little worried, but we'll see here. I'm actually very worried because I know what's supposed to happen. We plug in 2, 0 here, I get negative 4 times 4, which is, oh good, negative 16, plus 0, plus 16, minus negative 8 times 2 times 0. And we get 0, because this is something times, oh, that's 0, minus 0. We're not thrilled about 0 because 0 means we don't know, right? It's unknown. And that's okay. For that question, they just ask you to classify either it's a max, a min, a saddle, or unknown. Now the question is, and this is the part that I think is kind of interesting, how do we classify all the points where, what was it, x squared minus y squared minus 4 equals 0? Yeah. It seems tricky because I literally don't have the time to test every single point. So here's what we're going to do. We're going to be sneaky. We're going to try and make this show up in D. So I'm going to look for making x squared minus y squared minus 4 show up. Or maybe 4 times it. 4x squared minus 4y squared minus 16 equal to 0. Right? If this is equal to 0, so is 4 times it. Why would I pick 4 times it? Because it kind of looks like I might be able to get that to show up there. Here's what I mean. So just watch for a second and definitely don't, you're welcome to ask questions. Just give me a moment. So I'm going to take this 12x squared minus 4y squared minus 16, and I'm going to write it in a convenient way as 8x squared plus 4x squared minus 4y squared minus 16. Well, what do you know? That's equal to 0. And in a similar way, I can do the same thing here. I can say I'm going to write 8y squared plus 4y squared minus 4x squared plus 16. And even though it's the negative of that, it's still 0. Right? The negative of 0 is still 0. Okay, minus negative 8xy squared. So check this out. What happens? Well, I get 8x squared plus 0 times 8y squared plus 0 minus negative 8xy squared. But those look the same. 8 times 8 is 64. X squared times y squared minus negative 8 squared is 64. X squared y squared. Oh, holy smokes. That's 0 all the time. So here's what that means. It means that every point on this hyperbola, we don't know anything. We don't know if it's a max or a min or a saddle. It's unknown. It's still interesting. So here's my point. My point is your homework problem is very similar to this. Like when you find your D, which you should not multiply out, you can do a similar sort of thing and make an x squared plus y squared minus 1 kind of appear. And then that part's going to be 0. And then the leftover parts multiply out to 0. Kind of weird. Here's what's going on. Here's what the graph of this thing looks like. Not that one. That one. So check it out. There's the hyperbola. Right? The hyperbola is the bottom of this thing that's intersecting the xy plane. And as you can see, it's not those points. So those infinite number of points, they are a global maximum, the global minimum. Right? Every one of those points has a y value, or sorry, has a z value of 0. But we can't say that they're local maxes because they're not less than the things that are next to them. Right? They're also next to a minimum, which also has, so right, to be a local minimum, you have to be literally smaller than the thing that you're next to. And none of those are smaller than all the things they're next to, because some of the things they're next to are just also the same. But there is all of your undefined or unknown points. Yes, they are all global minima. I know this question isn't asking about global minima, but they are. And the way you can see that they're global minima is actually really, really easy. You can be like, oh, well, look, my function is something quantity squared. The smallest it could ever be is what? Could it ever be negative? Definitely not. So the smallest this function can ever be is 0. Great, there's all the points where it's 0. Those are the global minima. Those are where we have global minima. Now, I also did say there was a saddle point at 0, 0. And you might argue that, hey, James, we're not really seeing that. And I would say you're right. And if we zoom out, it's probably going to look super freaking crazy. Oh, my God. Ridiculous. I mean, it's kind of neat. But yeah, there's some wacky stuff happening at 0, 0, comma 16 is the y value, I think, right? No, is that a result function here? I forgot, sorry. Yeah, 0, 0, 16. If we made this just a little bit smaller, just because I'm curious, we made that a 1 instead to make it easier to see stuff. If we zoom back in a little bit. Yeah, it still looks bonkers. Oh, you can kind of see the saddliness of it, maybe. Yeah, you guys maybe can, I can see it. It kind of looks like, I mean, I know this is not the loveliest example, but it kind of looks like the crotch of pants, right? Going down one way, up the other way. Yeah, cool. In case you're curious. Here's what the homework problem looks like. So you can see, oh yeah, there's this circle of global minima where it's all going to be not defined or unknown, I should say, not defined. And in the middle there, there's your relative maxima when x and y are both 0. Right, it's up there. Okay. Hopefully that's helpful as far as your homework problem goes. It is a little bit tricky, but it's certainly manageable. Questions about this problem before we move on to some absolute maximums on boundaries? Oh yeah, we got okay, you can ask questions. It's allowed. It's encouraged. It's welcome. Okay, you can always ask them. All right, so let's talk about absolute maximum values on a closed boundary. And while I could certainly try to draw this picture, you guys know my pictures are not that good, so I'm just going to let Grant do the work for me. Here are some nice pictures. So here's what we're going to do. We're still going to do the work, but here's what we're looking at. Some absolute maximum minimum values on a closed boundary. We're going to look at the function f of x y equals x squared plus y squared plus x squared times y plus 4 on the region all points where x is between -1 and 1, or you can say the absolute value of x is less than or equal to 1, and the absolute value of y is less than or equal to 1, or y is between -1 and 1. So here is what our region looks like. X and y are both between -1 and 1. It's the entire square. So imagine a room where D is the floor, right? D is our region. Some people use R, some people use D for domain. And f of xy is the ceiling or our surface. X equals 1, x equals -1, y equals -1, y equals 1 are the walls of the room. And the question is, where could the highest or lowest points occur on the ceiling? So maybe your ceiling looks like this, and the highest point is somewhere in the middle. But maybe your house looks like this, and the highest point is at one of the corners. Or, let's just look real quick here. No, oh yeah. Or maybe even your house looks like this, where one of the highest point is on one of the walls, right? It's not at a corner, it's at a point between the two corners. So that's kind of the whole idea, is that we have to look for critical points in the region where we have a relative maximum or a relative minimum. We have to look for the corners to see if maybe those are where we have the highest point. And then we also have to look for critical points along each wall where we might have a lowest surface value or a high, or a highest surface value. So that's the idea. We have to look for kind of three separate things: critical points, corner points, and then the hardest ones to find are the wall points or the edge points. We have to look for between the two corners on your edges. There's sometimes another kind of point that is a critical point that we have to check. Yeah, it's kind of a lengthy process. Like it's not, none of it's really super hard to do calculation wise. It's just that there's a lot of pieces to deal with. And then after we find all those pieces, the critical points, the corners, and the wall critical points, we're then going to throw them all back into the original function and see which one of those gives us the biggest output, because we want to see what's the highest point on the surface and which gives us the lowest point, or the lowest point on the surface. It's definitely something we did, I think, do in 17a, except we did it for functions of one variable, and then we see like, oh, is it the highest, like, in fact, I've got a picture right here. Is it the highest at some endpoint, like a wall or a corner, or is it the highest or lowest at some critical point where the derivative is 0? And sorry, you guys can't see that real quick here. You can kind of see it. In this particular not great drawing I've done, the absolute minimum would be right there, because that's the lowest point at a critical point, and the absolute maximum will be over here at the end point, because that's the biggest function value. So we're always testing back into the original function. Okay. Okay. Let's look back at our example, which I don't remember what I said it was. Our function xy is x squared plus y squared plus x squared y plus 4. And we're on the region, and I really just think it's worthwhile to draw it. Maybe draw it better than I'm drawing it. This edge is y equals 1, x equals 1, y equals -1, x equals -1. We already have 4 points we know we're going to have to check. F of 1, 1, f of 1, -1, f of -1, -1, f of -1, +1. We'll come back to that though once we do the rest of it. So let's go ahead and find the critical points. So I'm going to take my gradient. Let's go ahead and write it as the gradient. Sure, why not? Which is going to be 2x plus 2xy, and fy is going to be 2y plus x squared. Okay. We're going to set that equal to 0, 0. Now, I usually try and pick the easier piece to deal with. The second piece is not the easier piece. If I'm setting 2y plus x squared equal to 0, I'm not actually getting any values. And all I really know is that, well, okay, 2y has to equal negative x squared, or y has to equal negative x squared over 2. But I don't actually get any specific numbers from that. And I would rather get specific numbers off the bat if I can. So what I should have started with was saying, oh, 2x plus 2xy has to equal 0, which that can factor. I can definitely factor out a 2x. I'm left with 1 plus y. So what are my two? So I want to say, right, I really want to make it clear, 0, negative 1 is not a critical point. Right? If x is 0 and y is negative 1, both of those make this 0. Neither of those make this 0. Not together anyway. So either you get x equal to 0, or you get y equal to negative 1. And then we're going to use that in the other equation. So in my red equation here, if x is 0, then we're going to get 2y plus 0 squared equals 0. So y has to be 0 as well. So when x is 0, y is 0, that's our critical point, or one of our critical points. And then if y equals negative 1, well, then I have negative 2 plus x squared equals 0. So x squared equals 2. So x equals plus or minus the square root of 2. So I either get x being root 2, y being negative 1, or x being negative root 2, y being negative 1. And now I should make an important observation. These 2 points are trash. They're not in the domain. They're not in, or I should say, they're not in the region. They're definitely in the domain of the function. They're not in the region that we are concerned with. Square root of 2 is bigger than 1. So these points are garbage. So the critical points you find need to be in the region you're actually limited to. Okay. So great. We're also going to look at f of 0, 0. And then we have to deal with all the walls. Do I have room? Yeah, I probably have room. Let's go over here. So the walls. Itchy nose, itchy nose. Okay. So we're going to start, let's start with y equals 1. That's one of our walls. For y equals 1, we're just going to plug in y equals 1. Oh, sorry, thank you. So when we plug in y equals 1 to the original equation, or the original function, we get f of x comma 1, and it's going to be x squared plus 1 plus x squared plus 4. And then we're going to simplify. And then we're going to take the partial. So the partial is 4x. We're going to set that equal to 0. And we're going to end up getting x equal to 0. So 0, 1, right, because y was 1. So 0, 1 is another pseudo-critical point. It's not really a critical point, but it's a critical point if we're restricted to being on this wall. And then we're going to do the same thing for every other wall. So if y equals negative 1, let's see, we're going to have x squared plus 1 again, minus x squared times 1, or minus 1 times x squared, plus 4. And sorry, I forgot to write the function. That's f of x comma negative 1. And that's just equal to 5. And if we take the derivative of that, the derivative is just 0. Which means it's kind of constant on that whole wall. So on the wall y equals negative 1. Sorry, brain. Yeah, just want to make sure. So since this is constant, You could have just really looked at that. We have no points to consider. Right, one end of the wall, the other end of the wall should be the same height, right? Because literally, so what's happening here is on this wall, the function is always at a height of 5. So none of those points could really be, unless they're all the maximum or all the minimum, none of those points are going to be the maximum. And we'll see if we test the corners. All right, let's look at f of, now we're going to look at this wall, 1 comma y. That's going to be 1 plus y squared plus 1 times y plus 4. And then we're going to take the derivative. Fy is going to be 2y plus 1. So we're going to get y equal to -1/2. So 1 comma -1/2. That's another critical point. And then finally, the last one, we're going to look at f of -1 comma y along x equals -1. And we're going to get, let's see, the same thing actually. We're going to get 1 plus y squared plus 1 times y plus 4. And we already know that when we take the partial and set it equal to 0, we're going to end up getting y equal to -1/2. So -1, -1/2 is also a critical point, at least for a wall. It's a lot of work. I don't envy you. It's a lot of work. So now we have to go back and check all of these. So we're going to plug each of these into the original function. Let's do it quickly. So f of 1, 1 is going to be 1 plus 1 plus 1 plus 4. F of 1, -1 is going to be 1 plus 1 minus 1 plus 4, which is going to be 5. -1, -1 should be 1 plus 1 minus 1 plus 4, which is going to be 5. -1, 1 is going to be 1 plus 1 plus 1 plus 4, which is 7. F of 0 is 0 plus 0 plus 0 plus 4. 0, 1 is going to be 0 plus 1 plus 0 plus 4, which is 5. And then these last couple, okay, if I plug in 1, -1/2, I should be a little bit more careful here. It's going to be 1 plus 1/4. 1 times -1/2 is -1/2 plus 4. That's going to be, let's see, 5 plus 1/4 minus 1/2. That's going to be 4 3/4, or 4.75. And then finally this one, -1, -1/2. I get 1 plus 1/4. X squared is 1 times -1/2 is still -1/2. It's the same thing. Okay. Which one's the biggest? So fair enough. Yeah, so which value is the biggest? 7. So we have absolute maxima or global maxima at 1, 1 and -1, 1. Which one's the smallest? 4. So we have an absolute minimum or a global minimum at 0, 0. We have absolute maxima or global maxima at both 1, 1 and -1, 1. Interesting. I wish I could draw it for you, but it would probably look terrible. But you can imagine, so this is, yeah, these 2 points here at 1, 1 and -1 is where the roof is the highest. And here at 0, 0 is where the roof is the lowest. So I'm going to make an attempt. If we try and lean this back a little bit, like, okay, this is not perfect, but it might look something like something like that, where this point here is lower than all the rest, and these points clear the height. So this would be like 1, 1, comma 7. This would be like negative 1, 1, comma 7. And that point there would be like 0, 0, comma 4. I think that kind of demonstrates it, maybe a little. Hopefully. Can you explain 5 again? What did you mean by no points to consider? Good question. So that's actually being kind of demonstrated by this thing I just drew right here, which is that for y equal to -1, right? Because that's what we got. Yeah. The function f of x comma -1 was equal to 5, right? Because it ended up being, I'm just looking back at the original here for a second, sorry. If I plug in -1 for y, I get x squared plus -1 squared plus x squared times -1 plus 4, and those end up canceling, and I just get 5. So no matter what x is along the line y equals -1, I get the function value of just being 5. Meaning it's very unlikely that we have an extreme value there. We still don't have any critical points. And what'll happen is if we end up seeing that this point here and this point here, if both of those corners end up being a maximum or a minimum, we'll know that every point in between was a maximum because it was a constant on there. It's not very common, but that's what's happening there. Okay. Yeah, we got time. We definitely got time for another. And so when you're looking at a function on a restricted domain, some region in the XY plane, 3 things to consider, which ends up being usually like 9 things to consider. Critical points, corners, and critical points on the walls. So let's look at another example. Let me make sure I don't want to lose all the stuff. Keep things in order so I can, yeah. Let's do another one. Now we want to find all the global extrema of this function of xy equal to 1 plus 4x minus 5y over the region, which is going to be the triangular region, bounded by the following 3 corners: 0, 0, 2, 0, and 0, 3. And I always think it's a good idea to draw the region. So 1, 2. So there's my region. Let's talk about the things we need to evaluate the function at. So we've definitely got our corners, which are already listed there. And then let's look at the critical points. So I'm going to set fx and fy, gradient, if you will, equal to 0, 0. But what's fx? What is fx? Everybody should be able to tell me what fx is. It's like a 1-word, 1-number answer. 4. Fx is 4. Which might already indicate to you, oh, we're not going to get any. Right? If fx is always 4, this can't ever equal 0. And fy similarly is going to be -5. I should point out this function is a plane, And a plane, right, is unless it's a flat plane, which is not. A plane kind of just slopes, upward or downward, whichever. There's not going to be any humps, right? There's not going to be any relative extrema in a plane because it's either always going up or always going down. So we're not going to get any critical points here. Kind of like a line, right? A straight line doesn't have any critical points because it never turns directions. Okay, let's check the walls. So what are my walls? Well, there's one wall, y equal to 0. There's another wall, x equal to 0. And there's another wall whose equation I should find. Let's see. So the equation of this wall, I can see the y-intercept is 3. I can see the slope is down 3 over 2, or the rise over run is negative 3 over positive 2. So it looks like the equation of my line there is y equals negative 3 halves x plus 3. I'm pretty sure that's right. Right, my slope is over 2 down 3, or down 3 over 2. And yeah, that's right. So then we're going to take each of those and plug them into the original equation and set it equal to 0. Or sorry, set the partial equal to 0. This might not result in anything. Let's check. So f of x comma 0 is equal to 1 plus 4x. And if I take the partial of that, nope, not interesting. It's still just 4. Do I get the same thing here? Probably. Depends. Well done. F of 0 comma y. I said that, well, that's going to be 1 minus 5y. And yeah, that partial is also not particularly interesting. Negative 5, which is never 0. And then finally, if I plug this in, that might be more interesting, but I'm not counting on it. I'm going to get f of, so here's how I would write this. I would get f of x, and it's going to be, so I'm just plugging in this for y. So it's going to be 1 plus 4 times x minus 5 times negative 3 halves x plus 3. And let me ask you, I don't need to take the derivative of this to know, oops, sorry. Looking at this, what's the highest power? What's the only power of x? So the derivative is going to be what kind of thing? A constant. So I don't even care what that is. F prime of x is going to be a constant, which is not going to be 0. I mean, it could be 0, I guess, but it's not. It's definitely not because you got a 4x and a negative 3 halves x. So again, no critical points there. So we'd be happy to see this question on the test because there's not a bajillion things to check. So we're just going to check the corners. F of 0, 0. Grabbing this pen is not good. Is 1. Sorry, you guys can't see the function. There's the function up there. Is 1 plus 0 minus 0. F of 2, 0 is going to be 1 plus 8 minus 0, which is 9. And f of 0, 3 is going to be 1 plus 0 minus 15, which is negative 14. So it looks like there's our absolute maximum. So max at 2, 0. And there's our minimum. Minimum at 0, 3. Should we do another one? This one felt kind of disappointing. I mean, I know it was disappointing, just like kind of lame. Like, all right, that one's fine, I guess. But it does. So the point though is that it does happen sometimes. And sometimes your function is just, oh, it's never equal, or I should say, sometimes your partial is just never equal to 0, so you don't get any critical points there. Let's see. Let me look in the book. So I will point out that is literally an example from the book. That is problem 17 from section 9.6. None of these are super exciting. The problem is if we make something up, it could just be crazy. So fine. Let's be more interesting than that. But I guess interesting is not the point. Let's say we've got this function, which I'm going to change just a little bit. Let's say f of xy equal to, sure, 6x minus 8y minus x squared minus y squared. I kind of want to throw in a minus xy there, but I'm a little worried that's going to make it terrible, so let's not do that. And we want to find where this function has absolute max, absolute minimum. Sorry, you can't see anything. So on the domain where x is between -1 and 4, y is between 0 and 5. Again, a rectangular-ish region. Actually, I think it's a square region technically, but rectangular region. So here's our region. X is going from -1 to +4. Y is going from 0 to 5. So we're looking like this. Here's our region. There's the floor of our house. We were looking for what point in the house the roof is the highest and the roof is the lowest. Okay. We already have 4 points to check. Those 4 corners. You might just start off by doing that, although it's probably, I don't know. I kind of like to do it all at the end, so I'm going to wait. Let's find the critical points. So my partial with respect to x is 6 minus 2x. And partial with respect to y is -8. I'm a little worried. I might have to change things around so that things work out right here. I might just throw in the next negative sign. So setting that equal to 0, we're going to get x equal to 3. And setting that equal to 0 leads to disappointment. So I'm going to change it slightly. Change that to a plus. And change that to a plus. So now setting that equal to 0 leads to y equal to 4. Much more exciting. Nicer when the critical point is in the region. But if I hadn't changed it and we had gotten the point 3, -4, we'd just be like, oh, it doesn't matter. It's not in there. So if your critical point is not in the region, ignore it. So our critical point is the one and only 3, 4, which is about right there. And then we have to test the walls, which is always kind of I think it's the hardest part, honestly, testing the walls. So the walls. So let's start with y equal to 0. So if y equals 0, people often just say, well, if y is 0, I'm just going to write this as a function of x. F of x is going to be 6x plus 0y minus x squared. And the derivative is going to be 6 minus 2x equal to 0. So we're going to get x equal to 3. So not surprisingly, well, maybe surprising, I don't know. It could be surprising or not. Y is 0, x is 3, so we're over here. You don't have to graph these. I just like to graph them because I think it's helpful. And then it might not even be that helpful. I like it. Let's also do y equal to 5. So if y equals 5, it's not going to really change anything. And that's actually something that's worth observing. If you're plugging in constants for one of the variables, oh, well, so it could change something. It's not changing. So for example, I'll just point out, if you had like a term where you had x's and y's together, like if you had an x, y term, then plugging in 0 for y would make the derivative of this non-existent, but plugging in 5 for y, the derivative of this would be 5. So I shouldn't say that, right? It does, you do get different things happening if you're plugging in y equals 0 or y equals 5. Just not in this problem. Because you're plugging in y equals 5, your function becomes 6x plus 40 minus x squared minus 25. But the derivative is still the same. It's still 6 minus 2x, which gives you x equal to 3. So we get the point 3, 5. And I wouldn't be terribly surprised. I would maybe be willing to bet large sum of money on it without looking that my other two wall points are going to be here and here because of the way the function is. I'm not positive, but I'm pretty confident. Let's take a look. So let's look at x equal to -1. X is -1. Our function is going to be f of y is -6 plus 8y minus 1 minus y squared. The derivative is going to be 0 plus 8 minus 0 minus 2y. And yeah, if you set that equal to 0, you're going to get y equal to 4. So -1, 4. And over here, it was the point 3, 5. And finally, at x equal to +4, the same kind of thing's going to happen. F of y is going to be 24 plus 8y minus 16 minus y squared. And the derivative, more importantly, is going to be 8 minus 2y, which means you're going to get y equal to 4. So the point 4, 4. So there are the 9 points we have to plug into this lovely function that we all adore. So this is the part that's kind of a pain. I mean, it's all kind of a pain. You could probably describe a lot of mathematics that way. It's kind of a pain. Yeah, I just need a new piece of paper. So here's what we're doing. We're doing f of xy. It's equal to 6x plus 8y minus x squared minus y squared. And we have to check the following points. F of, I don't even get any 0, zeros. Okay, fine. So -1, 0. F of, I'm not doing these in any particular order. I'm really just looking at my picture and going from the bottom to the top. So f of -1, 0, f of 3, 0, f of 4, 0. Sorry, you guys can see that. And then the y values all get to be 4. So f of -1, 4, f of -1. Sorry, f of 4, 4. I skipped one, and f of 3, 4. And then finally, the y values get to be 5. So f of -1, 5, f of 3, 5, f of 4, 5. This is where you hope they let you use a calculator. I mean, yeah, it's not like it's hard to calculate this. It's just not fun. So plugging it in, you get -6 plus 0 minus 1 minus 0. Okay, we got time to do this. Fine. Plugging in 3, 0, you get 18 plus 0 minus 9 minus 0. That's going to be 9. Plugging in 4, 0, you get 24 plus 0 minus 16 minus 0 equals 8. All right. It's going to get lovelier now. Yeah. So plugging in -1, we get -6, and 4 for y, we get 32, and then -1 minus 16. That's going to be something, 9, I think. 32 minus 16 is 16, minus 6 is 10, minus 1 is 9. Yeah. Plugging in -4, 4, we get -24 plus 32. You can see how this is kind of just dumb. Would you agree this is kind of just dumb? I mean, it's yeah. Those cancel, you get -24. Plugging in 3, 4, you're going to get 18 plus 32 minus 9 minus 16. That's going to be 50 minus 25 is 25. Okay, we're almost there. -6 plus 40 minus 1 minus 25 is going to be 40 minus 25 is 15, minus 6 is 9, minus 1 is 8. 18, 40, minus 9, minus 25. That's going to be a number, 24. And then finally, the last one, thank God, 24. 5 times 8 is 40, minus 16, minus 25. That's -41. 40 minus 41 is -1, plus 24 is 23. Woo! All right, so then we go, that's the biggest, that's the smallest. So we have a global minimum at -4, 4. We have a global maximum at 3, 4. hopefully, if someone asks you a question like this on the exam, the example is not too. And this example is like, this function isn't even that bad, right? That's like not a terrible function. It's just got a lot of critical points and endpoints and corner points. It's just.
Where do we get all those coordinates from for the X and Y?
So from 3 places. Place 1, critical points, setting the gradient equal to 0. We got the 1 critical point, 3, 4. Place 2, all the corners. Every corner is always a candidate to be an absolute max or an absolute min. So corner 1, corner 2, corner 3, corner 4. And then place 3, which is the hardest place, is the walls. So on each wall, the wall x equals 4, x equals -1, y equals 5, and y equals 0, I plugged in that thing into the equation. So for y equals 0, I plugged in 0 for the y's, and I got 6x plus 0 minus x squared minus 0. And then I took the derivative of that, set it equal to 0. So I got x equal to 3. But I should stress x equals 3 and y equals 0. And then I did the same thing for each of the walls. So I plugged in y equals 5, I got x equal to 3. I plugged in y equal to 4, I got, sorry, no, I didn't. I plugged in x equal to -1, I got y equal to 4. I plugged in x equal to, 4, I got y equal to 4. So that's how I got those other 1, 2, 3, 4 points. 4 walls, each having a point. Not every wall always has a point. Like in our previous example, none of the walls had points. Every corner, which there might be 4 of, there might be less of, and then any critical points. Daisy, right?
Yeah. I'm just saying the point was 4, but you didn't calculate -4.
Oh, I might have. Yeah, that could have been a mistake I made. Sorry about that. Yeah, you're totally right. 4, 4. It would have been, yeah, you're right. I did calculate -4. So be careful with your work. That should actually be a positive 24 plus 32 minus 16 minus 16. So that should actually be a positive 24, which means it is no longer the global minimum. Instead, the global minimum would be when we have a value of -7. So we have a global minimum. Thank you. Good catch. At -1, 0. All right. So interestingly, this happens a lot actually. This function does have one of its extrema at the critical point, 3, 4. Its other extrema is occurring at a corner, -1, 0. All right, I've said all the things. It's time to go.